Yeah, okay, so here we'll get started. It's 12:04. Thank you all for who are here. This is our fourth student alum networking discussion series. And this time we're having Jamie Maughan, who's one of our, I shouldn't say older alum. He's somebody who's been an alum for a long time, as opposed to some of the more recent alums we've had recently. So he can give a perspective on a long career. And in a minute, Candace Oviatt, who was his major professor, who herself is an alum, she's going to be introducing him. But I just want to say welcome to the series. It is being recorded. This part is being recorded so that you know. Jamie will talk for about 30 minutes. We'll have questions and answers from Jamie. And then after that, we'll ask the people who aren't students and recent students to leave so that Jamie can have more of a discussion with our present GSO and our recent undergraduates and give them some career advice and talk to them about that. So that's the format that we're going on. And also just to tell you, we're going to be continuing this series in June and July. And watch this space, actually watch your email for identifying who those people are going to be. So without further ado, I would like to turn this over to Candace Oviatt, who is going to introduce Jamie. Candace?
Thank you, Veronica. I'm here to introduce James T. Maughan to you. Jamie, I don't even know what the T stands for, but perhaps you could tell us at some point. You know, I don't have favorite students. Of course, I'm not supposed to have favorite students, but when I think about student accomplishments, Jamie always comes to mind. Jamie comes from Virginia. I think you can still hear sort of a lilt in his voice. He got his Ph.D. with me in 1986. He's had an illustrious career in environmental consulting, and he's passed this legacy on to the next generation by publishing papers, by writing books, and by teaching at several institutions, including the Harvard University School of Continuing Education. He's spent a dozen years teaching graduate courses on ecological risk assessment. He's written 2 reference and textbooks on environmental analysis and process methods. Jamie started out in biology and aquatic ecology. He got his BS from Old Dominion and an MS from Virginia Polytechnic Institute. For his PhD, he participated in mesocosm experiments examining the impact of sewage sludge on the estuarine environment. He worked in our famous MERL mesocosms, which were miniature physical models of Narragansett Bay. He evaluated the impact of the sludge on bottom animals in the mud. I have to say it was one of my least favorite experiments. Jamie went on to publish papers based on his dissertation, and this is always the mark of a successful PhD student. Jamie went on to a prestigious consultant career with top-rate consulting companies. He worked for CH2M Hill and Metcalf and Eddy. He worked on water pollution abatement. He worked with hazardous substance contamination and remediation. He addressed social concerns and developed plans to minimize the impacts of transportation and other infrastructure projects. And he has been involved with dozens of environmental impact statements and probably hundreds of National Environmental Policy Agency documents. He's been a senior advisor to the U.S. Department of Transportation, environmental nonprofit companies, and currently serves on many local government boards and commissions. With his career in environmental consulting, Jamie has done what you hope all your students will do. He has used his education to improve the environment and mitigate the impacts of urban and industrial pollution all over the world. So, Jamie, I look forward to your talk.
Thank you very much, Candace. Let me share my screen and then we can begin. There. So again, thank you, Candace. I hope I can live up to that introduction in my talk today. And also, I always wonder why I've been gone from GSO about 35 years and I've aged, but you're still the same age you were when I left. So just to add to my background that you mentioned, the T in my name stands for Tillman, which is also the name of an island in the Chesapeake Bay, which is where I became interested in marine biology in the Chesapeake Bay, and long history of family there. And thank you, Veronica, for asking me to do this. I really am looking forward to it. I love talking about my research and I love sharing what I've learned and sometimes the mistakes I've made so people can learn from them throughout my career. So I'm going to start off talking about the research that I did at GSO and how that research propelled me directly to my first environmental consulting job, which was a major project for several years, and then how that first project then created a career first in consulting and then a multifaceted career that as I think I'll share with you has provided me with some great opportunities. So first, before I talk about the research I did at MERL, let me give you a little background. I did some consulting before I ever came to GSO, and I was involved in wastewater management during that time. So the background is that in the early 70s, during the early environmental movement, the first Earth Day, the Clean Water Act was passed in the early 1970s. And one section of that Clean Water Act, Section 201, recognized the need for management of municipal wastewater. At the time, less than 80%, excuse me, more than 80% of the municipal sewage or the municipal wastewater in this country was discharged to the surface water with little or no treatment. In recognizing the need to manage that huge amount of pollution, Congress, in their wisdom, funded upgrading of all the municipal sewer systems in the country at a price tag at the time of $250 billion, which in today's dollars is well over $1 trillion. It's one of the biggest infrastructure programs ever put in place. And it's something that needed to be done right away. There wasn't time to do the research to determine exactly what needed to be done. We knew enough at the time in the early 70s to know that the biochemical oxygen demand, or the BOD, or the organic matter in the sewage was the biggest problem. It was depleting the oxygen in the surface water, causing anoxia and fish kills throughout the country. So to kick off this huge $1 trillion program, the EPA, which administered the program, required treatment of the BOD, of the organic carbon in the sewage to improve the oxygen conditions. And it had a big effect. And we were able to hit the biggest polluters, municipal sewage systems in the country, and upgrade them. But it soon became apparent that in many systems, particularly in estuarine systems, just controlling the BOD wasn't enough. We still had a problem with nutrients, and we had a problem with the solids in the municipal water. Whereas for BOD, we had a pretty good standard. We knew what DO levels were required to support marine life, but we really didn't know appropriate levels of nutrients, which were acceptable and which was too much. Similarly, we didn't know exactly how much carbon deposition on the sediment would cause problems and disrupt the ecosystem. So EPA, again in their wisdom, decided to fund research to address this need to understand how much carbon could be deposited in the sediments and how much nutrients could be added. And they funded MERL. And that was the origin. It's been used for other things since then, but this looking at enrichment was one of the major reasons for MERL to be funded. And just to spend a minute for those of you who aren't familiar with MERL, as Candace said, it's a mini Narragansett Bay. They were over a dozen of these tanks, and they were controlled with regard to temperature, mixing, exchange, to replicate Narragansett Bay. And we had these 12 or 14 replicate systems that could be treated differently to see the response. And critical to the operation of MERL was having somebody watching over us to make sure we perform good science, and that of course was Candace. So she was our boss, and she sat right there and looked at her window and saw those MERL tanks every day and kept us in line. One thing we found out early on in the MERL experiment, which we knew, but we found out again, was that the sediments in those MERL tanks were critical. You couldn't just add mud and expect to have an Narragansett Bay or an estuarine sediment. That sediment had a very distinct chemical, physical, and biological structure, and we needed to replicate that precisely in order for those MERL systems to form as Narragansett Bay did. So we went out in Narragansett Bay every time we started an experiment, and we used this huge box core to take out these intact sections of sediment, almost a meter in thickness. And then we placed them in a tray, kind of like a jigsaw puzzle. And then we lowered that tray into the bottom of the MERL tanks. And just to prove I was there, I'm pretty sure that's me, because I still have that sweater, and I'm pretty sure that's Candace standing there, and that might be Eric Kloss. But anyway, that sediment was a critical piece, not only to certainly to the operation of the MERL systems, but also reflects the importance of sediment in an estuarine system, and directed me toward my work in research. Another critical piece of those MERL systems was that we could monitor those systems because they were enclosed, and we monitored the hell out of them. We looked at the water column, we looked at the sediment, we looked at the biota, and we looked at the processes such as benthic oxygen demand, nutrient uptake, the different sources of food for the different animals. And each one of these segments of the MERL ecosystems were monitored, some of them daily, most of them weekly, some of them less frequently. But we had, and maybe I'm exaggerating for emphasis, but we had a good quantitative handle on how that system was working and how the exchanges occurred. And just for those of you who haven't seen it in full operation, it's a beautiful picture of MERL. And another reason I want to show this picture, see all those people standing out there? Those plus those back in the lab were our MERL team. And that team and the teamwork was such a critical piece of the research. Each of us had our own piece, but we shared it with everybody else. So it gave particular importance to doing good work, not trying to cut corners, being able to share your information because you needed the information from the other team members to understand how that system worked. And that appreciation and experience in teamwork, I think, has been important in my career in consulting or anything else, because things are really only achieved as a team effort. And that set the foundation for me to participate and be part of a team. So the initial and some of the major experiments that were conducted at MERL were enrichment experiments. Again, to look at that addition of nutrients and solids to the marine ecosystem. And what the objectives of those experiments were to measure the response at an ecosystem level, as well as the various components to that enrichment. And from those measurements, to be able to quantify nutrient and solid input levels and relate them to how they changed the ecosystem and how they degraded the ecosystem. Marine scientists have known for a long time that adding nutrients or adding carbon is at high levels is going to be detrimental to that system and eventually cause collapse. What was missing was a strong quantification of how much nutrient, how much solid input cause those conditions of change or degradation. And MERL provided the opportunity to quantify that relationship. Then with that scientific information from those enrichment experiments, the EPA and others could establish what levels of addition of nutrients and carbon to a system could be acceptable and what could be unacceptable. So with MERL as the perfect opportunity to look at a gradient so we could quantify how much is too much, how much is way too much. So we took our MERL system, we had controls, we ran some of the tanks as controls, and then we added nutrients or sewage sludge or sewage sludge to the various systems to show a gradient. We had a low addition of 1x, which represented approximately the average amount of nutrients and carbon going into Narragansett Bay, up to 4x, and in the extreme case, up to 32 times that amount of nutrient and organic matter. This wide range from 1 to 32x generally represented the rate of loading to temperate estuaries, particularly on the East Coast. So we had that span, we had that gradient or spectrum of the various estuaries, and we could monitor the response to each one of these levels. In the experiment that Candace spoke about, the sludge experiment, which I'm going to focus on, we only went up to 8x. And but other nutrient experiments went up to higher levels. So as you might expect, and as we knew from the literature, as we added nutrients, which is the top graph here, in the early months of the experiments, we saw the oxygen levels increase drastically. This was due to the increased primary production from the addition of nutrients. However, as that experiment proceeded in time, that increased primary production was respired and lowered the oxygen levels. And in the highest addition of nutrient systems, represented by the solid line, it was below the envelope shown in red of the DO in the control tanks. So we saw the result of that nutrient enrichment, and critical to notice here is that we saw a gradient. The more we added to the system, the higher the rate. And since we could quantify it, then we had a scale to use to see how much nutrient addition was acceptable and how much was too much. In the sludge addition treatments shown in the bottom slide, we saw a somewhat different pattern. In the early part of the experiment, even though primary production was drastically increased due to the nutrients, the respiration of the sewage sludge kept the dissolved oxygen levels low. And what we saw through the course of the experiment was that the respiration of the combined accelerated primary production and sewage sludge resulted in severely decreased dissolved oxygen levels. And in the 8x treatment, again shown by the solid line, the tanks actually went anoxic and we had mass mortality. But again, we have a scale here. We see how much we can add and get a little decrease or a big decrease or total Armageddon, if you will. And of course, I cherry picked this graph, but we looked at the response of the benthic animals and the benthic system to carbon addition. I picked Polydora, which is a spionid surface feeding polychaete, because we had the best R square, but all of them were pretty good. What we saw, as you can see in this graph, both for abundance and for biomass, as we add carbon to the system, the benthic population goes up, which again, we expected, and other studies have seen that, but now we could quantify it. We could see an increase in production associated with the amount of carbon going into the system. So we now had a scale, we had a measurement tool, we knew what would be the response of the system by adding certain amounts of carbon. So then what we did was develop that scale, develop those criteria, which resulted in this chart. Again, we knew from the literature that as you add more carbon, the system is going to change, but it wasn't easily quantified in the field because there are so many other variables. With looking at field data in combination with our MERL data, we were able to develop that scale. If you're adding carbon in grams carbon per square meter per day, less than about 0.13 grams carbon, you're going to have a normal system, which was represented in the MERL controls. If you added carbon, combination of primary production and sewage solids, above 0.3, then you start to get a change system, which was represented in our 1X, or in the field, a change system. So that amount of carbon resulted in a change in the biological community. In the MERL case, for example, we went from about 30% of a type of benthos that feed on the surface, which you might want to consider pollution tolerant, up to 50%. The biomass and the abundance increased by around 50%, or somewhere between 130 and 270%. This was a change system. Once you went to carbon deposition over about 1.34 up to 3 grams carbon per square meter a day, you started to get a degraded system. Your dominant benthos by pollution tolerant shifted from about 30 to 70%. The biomass was up 200 to 400%, and the abundance similarly went up. So we now had a scale. We understood how the system would respond as you added carbon. And from this point is when I graduated from GSO and went out to the consulting world and was worked on a project for Boston Harbor, which you see in this picture. The cleanup of Boston Harbor, which I worked on for about 5 or 6 years, was critical to my career, but it also was a critical project. At the time, Boston Harbor was deemed the dirtiest harbor in the country. It was actually part of the 1986 presidential election when then Governor Dukakis was running against Bush Sr., and Bush attacked Dukakis for having the dirtiest harbor. So it was critical to clean this up. And the problems in the harbor were that up to 1 billion gallons of sewage was going into the harbor every day. And that sewage was either not treated or totally inadequately treated. And even though what treatment occurred was to remove the sludge from the wastewater, that sludge was put back into the harbor. There was limited circulation because the discharges in that Boston Harbor were just a few dozen meters from shore in shallow water. This resulted in anoxia throughout the harbor with fish kills, eutrophic conditions, and tremendous sediment carbon buildup. If you could have seen the sediment in Boston Harbor, it wasn't a pretty thing. It looked very much like the sludge we were adding to the MERL tanks in our experiment. So the challenge for the cleanup of Boston Harbor was to determine the level of treatment required for that 1 billion gallons a day of wastewater and where that discharge would be. Even though there were a number of factors, water quality, commercial and recreational species, cost, as factors to determine the appropriate level of treatment and location of the discharge, it turned out they were 2 critical elements. One was the sediment enrichment, and one was the water column enrichment. And there I was with our MERL data and our GSO data to help address those issues. What we did first in that cleanup was, of course, a mathematical model of Boston Harbor and the eastern offshore area. And from that model, we were able to predict what the sediment deposition as well as the water column concentrations of nutrients would be. So we were able, for each one of these green dots, which represents a potential discharge location, to predict the deposition of carbon on the bottom for various levels of treatment. And once we could predict the amount of carbon deposition, we could then compare it to the scale or the measurement tool or the criteria that we had developed to find out what was acceptable. And when we applied this measurement to those predicted levels of carbon deposition on the bottom, what we saw that discharges close to shore had very large area of what we considered a changed benthic community, and also a large area of degraded. As we moved offshore and got to areas of greater dilution in current, the deposition was less. Once we got out 9 miles to a depth of about 106 feet, we saw a controlled or smaller area of changed benthos and almost no area of degraded benthos. Similarly, with the nutrient addition, we saw discharges close to shore where the nutrients would be trapped to close most of the harbor in a tremendous area of change conditions and an area of degraded conditions with regard to primary production or eutrophication. As we moved offshore, the situation improved. And based on these two critical categories of water column enrichment and sediment enrichment, we were able to select a discharge site which was acceptable. And that treatment at Deer Island here in Boston Harbor and the discharge 9 miles out was completed in around 1990, and we've been monitoring it continually ever since. And we've seen that the conditions are actually better than we predicted. When we made our predictions, we were somewhat conservative because there was a fairly large error bar and we wanted to be on the safe side. And the monitoring has shown that those criteria we use for nutrient buildup and for sediment deposition of carbon were accurate, and the community stayed healthy. So that is the evolution of about 10 or 15 years of MERL experiments coming to real life, but it didn't stop here in Massachusetts. It proceeded to the shores of GSO in Narragansett Bay. Narragansett Bay had a eutrophic problem and a DO problem, and RIDAM, our Rhode Island Department of Environmental Management, was mandating that the Narragansett Bay Commission and the Fields Point Treatment Plant in Providence reduce their nitrogen load to the bay. It was an expensive process and expensive endeavor to reduce that nitrogen levels. And you can see in this curve where we show the reduction in receiving water concentration of nitrogen in milligrams per liter from about 0.45 down to about 0.3 at the upper end of that. To achieve that total removal, we're talking 88 million and less at a lower level. So looking at this curve, it became obvious there was a knee of the curve. We could reduce significantly by 0.08 milligrams per liter for $21 million, but to get an additional reduction of only 0.005 would be an additional $67 million. So it made sense to look at that knee of the curve. And RIDAM and others tried to model the nitrogen dynamics in Narragansett Bay. They were unsuccessful, with the question being, is this an okay level? They reverted to MERL data, empirical data. They looked at that 1x to 32x addition of nutrients to see what would be an acceptable level. And by looking at that data, they determined that this knee of the curve, an expenditure of about $21 million, should be adequate. So Fields Point was upgraded to this level and monitored, and so far, knock on wood, it's been acceptable. And they've been able to save about $50 million and devote that to such things as stormwater and combined sewer overflows, which I think, as Candace will tell you, is also a significant problem. But using, again, that MERL data. Just a couple of other things I want to touch on, and I won't go into any details because I'm almost at the end of my time. But my career from that Boston Harbor and Narragansett Bay work involved many other projects. One that I worked on for about 5 years was in the Great Lakes. Being an East Coast guy, I didn't appreciate the Great Lakes until I started working on this. First, from an economic standpoint, the Great Lakes were really the system that drove the industrialization of North America, of both Canada and the US. It's an amazing system when all the raw materials for steel production are around the shores of the Great Lakes. But equally as important, you can transport those raw materials to central locations like Cleveland or Gary to produce steel. And this really drove the economics of the US and the industrialization in the late 1900s and early 20th century. But shipping this material was done on these Great Lake carriers. And the problem was these Great Lake carriers spilled in unloading of the coal, the iron ore, and the sandstone. And this was washed for over 100 years into the Great Lakes, which turned out to be a violation of the Clean Water Act and the treaty with Canada. So the Coast Guard was charged with developing regulations to manage this sweeping of the ships to put the residue in the Great Lakes. And the charge from Congress was to balance the economic viability of the shipping industry, and with it the steel industry, and the environmental concerns in the Great Lakes. So again, we worked for years to look at this. We looked at where these sediments, where these dry cargo residue had been deposited throughout the Great Lakes. We went and we sampled with sonar to see where they were. Then we took samples, and we were able to sample the benthos again in these areas to see if it was changed from the control situations. We also did chemical and toxicity studies on the material. And what we found was, after 100 years of this sweeping of the decks and the deposition of coal, iron ore, which is also called taconite, sandstone, and other materials, really had not changed the benthic situation, with one minor exception. And that minor exception was the invasive zebra mussels. So we looked at zebra mussels to see what caused those zebra mussels who could attach to those particles. We found out there was a concern, but as long as the deposition of this material to the Great Lakes didn't get any worse, that the situation with the mussels wouldn't get any worse. And we were able to, working with the Coast Guard, establish regulations, which, again, knock on wood, has been very effective. One other study I'll just briefly touch on is for a gold mine in Juneau, Alaska, shown in the yellow dot here. This was a mine that was going to be reopened, and reopening of the mine necessitated the generation of 80 million tons of mine tailings, or crushed rock, where the gold and other valuable metals had been extracted. There had to be a way to get rid of this 80 million tons. We looked at many, many ways and found out that the one with the least environmental impact was to discharge that 80 tons to the surface waters. Not that it had no impact, but it was less than the other alternatives. So we spent several years looking at the depth, how to dispose of this material in the waters off of Alaska. Again, we modeled to determine the rate of deposition of this 80 million tons, and looked at what impact it might have. What we found from our model we developed was that the problem, of course, again, would be on the benthos, where we lost habitat and particularly food source for critical species. So we went out and sampled, which included such things as putting radio collars on tanner crabs and try and find a tanner crab's neck to put a radio collar on. It's quite a feat. We also went down in personal submersibles to look at the area. We understood that ecosystem, what the top predators were, what their food was, and the academics on the project developed this food web model. Looks like something might come out of GSO, out of maybe Scott Nixon's lab. But what we found was it was too complicated to work with. So we simplified it as consultants, being very practical. And for each key species, of which there were about 6, we developed a simplified model, and then we could analyze what the impact would be. So that was just two projects plus Boston Harbor that I've been involved in. It opened up to me what I consider a rewarding and great career in consulting. I've been able to work at last counted in 43 different states and 11 countries. I've been able to use the expertise and the understanding of how regulations and politics work to do environmental advocacy work, both in this country as well as in South and Central America. I've been able to do some environmental policy work. As Candace pointed out, I spent about 4 years as a senior advisor to the U.S. Department of Transportation on environmental issues. The other benefits, of course, are the travel. Being able to work with people of different expertise from different parts of the world has been extremely rewarding. Not to mention the projects in the South Pacific where I was forced to snorkel and scuba dive for weeks on end. Also, not to emphasize, but the pay as an environmental consultant can be pretty good, can be pretty rewarding. But again, to something Veronica said, we all are academics to some degree, and of course, when I jumped into consulting, I felt initially that I was giving up the lifetime goal of being in academia, but it turns out that was not the case. Based on what I'd learned and what I'd been able to accomplish in consulting, I was asked to teach, and as Candace said, I've taught for the last 20 years, just one course a semester, but I've taught for 20 years at Tufts and UMass Lowell and Harvard Extension, and it's been rewarding to interface with the students. And also publications, as Candace pointed out, I have been able to produce a couple of textbooks, one in ecological risk assessment, one in environmental analysis. And when my wife asked me when I'm going to publish another book, I said I only know 2 things, and I've published on both of them. So, but I have been able to do to stay in touch with academia and publishing. And just to conclude, one of my favorite pictures of MERL, we added that sewage sludge and nutrients by hand because graduate student labor was very, very cheap, and it was easier than building a machine to add it. So we went out there every day and added it. And also just to verify that I am a Benthic guy, there I am collecting cores, and here I am up in Maine at the Maine Yankee nuclear power plant taking sediment samples. So with that, I will open it up to questions or comments, and those of you MERL alumni, if I missed something, please inform our audience what I missed.
Thank you very much, Jamie. That was great. That was good. So tour through MERL and how what you did as a grad student really led into your career, which I think is the important thing for our grad students to be thinking about. So any questions for Jamie? I mean, you can either put them in the chat or go ahead and talk to him.
Oh, hi, Jamie. Fantastic talk. I liked it a lot. And you did a lot of different things. And one of the, I have a few questions. One of them is like, the variety of things you have to do and the variety of agencies you have to deal with. Are there any skills that you have to develop or you had before that don't get developed at GSO that you suggest that we should like work on it in case we're looking out like that?
Well, I think the teamwork is critical. Being able to work with a team, and when you're with a team or you're dealing with a regulator, you don't always get your way. But working in a team and being able to compromise and knowing when to pick your battles, I guess, and determine what's important, that's critical. And also doing the homework, know the regulations, know the science. And something that I found important. I've worked on both sides of the table. I've worked with EPA. I've worked with industries. I've worked with other agencies. So I've been on both sides of the table, and in probably a dozen or close to a dozen of projects that I've worked with, and dealing with people and negotiating and understanding regulations and trying to come up with a solution with the problem. Other people on the other side of the table frequently have been fellow GSO alumni. And I've found that we can look at each other across the table in the eye. We can disagree, but we know the background. We know that we rely on good science, and it's a feeling of trust. And I think it's certainly true with GSO, but other scientists too. So develop that feeling of trust is important in dealing with regulators. Show that you're not exaggerating, show that you're relying on the science, and you'll find development of trust helps in working with other people.
Thank you. Yeah. I'll wait for someone else in case you don't want to like take all the time.
So go ahead and ask your question. There's in the chat.
All right. I'm gonna ask another one then. What do you decide? So when you go into consulting, you have to name your price basically. And I don't know about others, but me, I find like a lot of trouble like putting a value to my work or that kind of self-worth in terms of monetary value in the market. How did you went about that?
That's an interesting question. I think the simple answer is basic economics, supply and demand. There are a lot of consultants out there, so there's a pretty good supply. And so you typically base what you charge on the industry standard, if you will, because there might be people that do it cheaper, there might be people that do it more expensively, but once you develop a reputation, people that hire you understand that reputation, and they understand they're going to pay that, if you will, typical price for a quality consulting gig. So that's pretty much how it's done. And just as a logistics, more often than not, as a consultant, we work and get paid by the hour, just as an attorney would, for example. So you hire us to work on a problem, you give an estimate of how many hours it's going to take, so that's an estimate of how much it's going to cost, but you send your bills in every month based on how many hours that you worked. So that's generally how how it's structured. Occasionally you'll look at a big project and say, we'll solve this project for you for this amount of money, and if you can do it for less, fine. If you do it for more, you lose money. But that's more the atypical way to do a consulting project.
You enter like back and forths about pricing once you're like zooming into a job?
There's certainly some of that, but again, if you've established your reputation or you work with a quality firm, There's some acceptance that you've done this before and you know pretty much how many hours it's going to take. And if the person hiring you doesn't have that much money, then you just tell them, okay, we will do less. We're not gonna charge less than we feel we're worth. We'll just do less work and work fewer hours.
Yeah, that's like a hard part for me. Thank you.
Jamie, I've got questions that are related to that. So because you were working with consulting firms, did they come and look for you because of your background, or did you go and find them?
I guess the answer to that is both, Veronica. I had worked for Metcalf and Eddy for about 5 or 6 years before I came to GSO, and then as I was finishing at GSO, I thought I'd get a Nobel Prize and every academic institution in the country would be beating down my door, but that didn't happen. And Metcalf and Eddy knew that I was graduating, and they had a project up in Alaska and Boston Harbor that they knew I was suited for. So they came to me and asked me if I would come back. Throughout my career, I have explored going to work for other firms. But then again, just as an interesting point, being hired by the Department of Transportation as a senior consultant on environmental policy, I just published that book on environmental analysis, and somebody at Department of Transportation saw it, read it, and appreciated it, and contacted me to see if I'd come and look for that. So I guess in the early years, just like any place else, you have to beat down the door. But once you get in, it's a fairly tight community and you're known throughout. And so people tend to know you. And if an opportunity comes up, you either recognize it or another consulting firm will come and ask you to work on that project.
Thanks. That's good to know.
Another question that I'm often asked is and sometimes poked fun at, or at least hopefully in a joking manner, of being a biostitute, combination of biologist and prostitute, is your consultant. And they certainly are some consulting firms that are guns for hire, but the firms I've worked for, I like to think, are quality firms, and their reputation is more important than a particular project. And in my almost 40 years career in consulting, I've really only been asked once to compromise or slant the data. That's only one time. And another interesting fact is that that mine in Alaska that I talked about briefly, another firm had that project, and EPA delved into their work and found they were cherry picking the data to produce results that were only showed them in the best light, and they were immediately kicked off the firm and off the project, and we were hired because we had a strong reputation of not doing that, and it worked out well.
Jamie, I have a question for you, and it'll show you I've never changed my stripes. Would there be a possibility of a partnership with academia and the consulting companies to establish a MERL type facility somewhere to continue to research questions like this?
I really wish that could be the case, but the consulting companies generally don't have the money. They rely on the money from their clients. A better idea that I had but never really developed was to take somebody like Narragansett Bay Commission or the MWRA up in Boston, or one of the other, or maybe New York City, to help fund and a facility like MERL to help with their determining the necessary levels of treatment or addition or things like that. I think that could be a possibility.
Yeah, it's never happened, and I always kind of wondered why we couldn't establish a partnership like that. Mesocosms are still really popular in Europe, but here it's a dead procedure.
Right. When you look at that Narragansett Bay Commission, where by using the MERL data, the Narragansett Bay Commission was able to save $40 million. You know, that's a pretty good selling point to develop a facility like that for research. I know on the clean water side of MWRA and other purveyors of drinking water, they have research facilities in places at academia to research their level of treatment and the quality of water they're treating. So there's certainly that possibility.
Thank you, Jamie.
Hey, Jamie, I would like to ask you a question. I'm thinking about that we have lots of female graduate students and minority graduate students. Is there a good situation for them to enter in consulting as well as in academia? Sometimes it's not easy to get into academia. So I'm just wondering what you might say on that.
I wish I had a more positive answer for you, but I think consulting reflects our society, and it's not as open as I wish wish that it was to minorities and to women or other groups. There certainly is, at least in the past, there's been when you go for work for the EPA in the past, for example, they look at the structure and the number of minorities and women in your organization as they view whether or not they want to award you their contract. So that's a positive side, but it is not as equitable as I wish it was. I think actually in reflection in client organizations, clients I've worked for, like the Coast Guard or EPA or other government agencies, I think that is more diverse, both from a gender and an ethnic standpoint than consulting is. But I would like to think that that's changing, but I can't say that it has.
Well, just not to discourage students, I do have a daughter who is a vice president of Tetra Tech, which is a consulting company. So it can certainly happen.
Great, congratulations! You're right. It certainly can, and I congratulate you and your daughter. And I remember when she was born.
Oh, it's a different daughter.
Oh, one of the twins.
One of the twins. Yeah.
Okay.
Yeah. Right.
Actually, I think Randy told me she was at Tetra Tech last time I talked to her.
So Barbara, of course, keep our students informed if she's hiring or knows of your company hiring. Any other questions? I don't see anything in the chat. If we don't have any other questions, then we'll stop this part of it. We'll stop the recording and we'll go to our discussion with the students and recent graduates and people who have questions for Jamie. And so that being said, again, from all of us, thank you, Jamie. It was really